So basically, what we want to do is we want to square both sides as much as we possibly can. But we have to make sure that when we square both sides, we're actually squaring both sides and not just squaring whatever we want. In problem one, we're going to square both sides. So the square root of x squared is x, and 4 root 5 squared is 4 root 5 times 4 root 5. So that's 16 times 5, which is 80. So x equals 80. In problem number two, we square both sides, and we end up with x plus 7 equals 10. So x equals 3. Those were pretty innocuous. Problem 3, we just subtract 7 from both sides, and we get the square root all by itself. Then after we get the square root all by itself, then we'll square both sides and we get x equals 9. Problem 3 is where we start to get into danger zone, because if we think we can um, square both sides at the beginning, we technically can. It's just you have to actually square both sides. So if you wanted to square root x plus 7, you would have had to write root x plus 7 squared, do it twice, and it actually makes your problem much more complicated. You would have x plus 14 root x plus 49 equals 100, which does not make your problem any easier. Problem 4, I square both sides, so I get x plus square root of 2 equals 10. Then I subtract root 2 from both sides. X equals 10 minus the square root of 2. So those are the pretty straightforward problems. Now, after we do that, we have to actually talk about what happens when we square both sides. So, in a thought bubble on the side, we're going to go back to the quadratics chapter, and we're going to think about what happened if I had something like x squared equals 36. If I took the square root of both sides, I had to write my answer as plus or minus 6. That is because if I have x squared equals 36, if I graphed that, that's the same thing as graphing y equals x squared minus 36. So it's a vertical shift of negative 36. And what I end up with is I end up with two x-intercepts at negative 6 and 6. That's where these answers come from. So that's kind of what's happening. I had to make sure that when I took a square root, I didn't lose an answer. So I had to put plus or minus because there were two answers. And if I didn't put the plus or minus, I would only have one answer, even though I really should have two. Well, if I'm squaring, it's actually going to work the other way. Sometimes I might only have one answer, but when I square both sides, I might be adding an answer. I'll give you a really quick example. If I have x equals 3, if I square both sides, I get x squared equals 9, which, if I took the square root, I would have x equals plus or minus 3. That's a problem, because if I know that the original problem, x was only allowed to be 3, and then all of a sudden when I do some math and then do some more math, I've ended up with an additional answer, I have a problem. This is not good. So whenever I get answers, I need to make sure that I check for what we call extraneous solutions. We did this last chapter when we were doing rational equations, when we were doing fractional equations, basically. But we're going to have to do this in square root problems too. So I'm always going to check to make sure that any x value that I get doesn't violate any rules when I'm done with the problem. So I'm going to square both sides in number 5. X squared equals 4x plus 5, because when I square this square root, they basically are inverses of each other. Now I subtract 4x and 5 from both sides. And now I'm going to factor this equation. So I get x equals 5 and x equals negative 1. If I substitute 5 back in, I get 5 equals the square root of 20 plus 5. So that's good. But if I substitute -1 back in, I get -1 on the left equals a square root. I know this is going to be a problem. So I can't have -1 equals a square root. And what happens is if I sub -1 in, I get the square root of 1. -1 does not equal 1. As a result, only x equals 5 is an answer to this problem. Number 6, likewise, I will square both sides. So I have x squared equals -9x plus 10, x squared plus 9x minus 10 equals 0, x plus 10 and x minus 1 are the factors. So I get x equals -10 and x equals 1. If I substitute these things back in, I end up with -10 not working because -10 does not equal +10, but x equals 1 does work. Number 7 and 8. These are cubed root problems. So the cube root of 2x plus 1 equals 4. When I subtract 3 from both sides, I'm going to cube everything. So I get 2x plus 1 equals 64. Subtract 1 and I divide by 2. X equals 63 halves, which is the same thing as 31.5. If I substitute that back in, it's going to work. In problems like 7 and 8, it's much more unlikely to have an extraneous solution because when I cube everything, I'm not adding or subtracting um, positive or negative values nearly as much. Is it possible still? Yeah, but it's not nearly as likely as when I have a squared situation. So in problem 8, I'm going to cube both sides. X cubed equals 4x squared minus 3x. X cubed minus 4x squared plus 3x equals 0. Greatest common factor is x. I will then continue to factor. And I end up with x equals 0, x equals 3, and x equals 1 as 3 solutions. If I substitute all of these things in, 0 equals 0 works. 3 equals the cubed root of 36 minus 9. The cube root of 27 is 3, so that works. And 1 equals 4 minus 3. 1 does equal 1. So all of those work. Problem 9. I'll square both sides. Now, in this problem, when I square both sides, I have to be a little bit careful. 3x plus 15 does not equal x squared plus 25. I have to multiply x plus 5 times itself. So x squared plus 10x plus 25 using the distributive property. X squared plus 7x plus 10 equals 0 when I move everything over to one side. And now I'm going to factor. So x plus 5 and x plus 2 equals 0. X equals -5 and x equals -2 are my at least temporary solutions. Now I have to make sure that these things work. If I look back into the original equation, if I substitute -5 in, I get 0 equals 0. That works. If I substitute -2 in, I get square root of 9, which is 3, equals -2 plus 5, which is also 3. So both of these work. Problem 10. I'll square both sides. 19x plus 11 equals 3x plus 1 squared. I have to make sure that I distribute properly. So I have 9x squared plus 6x plus 1. Subtract everything over. I get 9x squared minus 13x minus 10 equals 0. And now I'm going to factor this. I will try 3x and 3x, and we'll see if that works. 5 and 2, so that would be 15 and 6. That's not going to work. 10 and 1 will definitely not get me to 13, so I need 9x and x. And if that doesn't work, then I guess we're going to use the quadratic formula. So 9 times 2 is 18, 5 times 1 is 5. That ends up giving me 13 when I subtract them. So I have x equals -5/9 and x equals 2. When I substitute these values in, I'll try 2 first because that's a little bit easier. 3 times 2 plus 1 is 7. So the square root of 38 plus 11 is the square root of 49. 7 equals 7. That's a winner. If I try negative 5/9, 3 times negative 5/9 is negative 15/9, which is the same thing as negative 5/3. Negative 5/3 plus 1 is a negative number. I can never have a square root equal a negative number in the real numbers. So negative 5/9 does not work. Make sure that you check for extraneous solutions all the time. Problem 11, we will square both sides. Make sure that you square 3 root x plus 1 by multiplying it by itself. So this ends up being 9 times x plus 1. It is very similar to this problem at the beginning, where 4 root 5 squared was 4 root 5 times 4 root 5. So I will continue. I squared the right side, and that's x plus 5. So 9x plus 1, or I'm sorry, 9x plus 9, use the distributive property, equals x plus 5. 8x equals negative 4. X equals negative 1/2. If I substitute these values in, I get 3 times the square root of 1/2 equals 5 minus 1/2, which is the square root of 4 and 1/2, which is the same thing as the square root of 9/2, which does equal 3 times the square root of 1/2. I don't need to simplify it anymore. I just know that it works. So x equals negative 1/2 is correct. A couple more problems. In a problem like number 12, you could square both sides in its current state, but that would make your life miserable. Instead, subtract the 2 from both sides. That will make squaring it much easier because now you don't have a square root anymore. If I squared it in its current state in the original problem, I would still have a square root when I did root x plus 18 plus 2 times root x plus 18 plus 2. I would still have a square root when I multiplied it all out. That's not something I want. So I subtract 2 from both sides. Now I can square both sides, and I get x plus 18 equals x squared minus 4x plus 4 when I square x minus 2. Now I will subtract everything all the way over to one side. So I get x squared minus 5x minus 14 equals 0. X minus 7 times x plus 2 equals 0. So x equals 7 and x equals negative 2. If I look at this and I substitute it in either to the red circled equation or to the green equation, which is essentially the same thing as what I started with, it's not like I did anything crazy like squaring both sides or anything. The 7 will work and the negative 2 will not work. 2 more problems. These problems are the 2 hardest. So if I look at both of these problems, there's no way that I can move the 2 in order to avoid continuing to have a square root in my problem after I square it. So I'll just square both sides at the beginning. I have x minus 7, so the part on the right looks good. Part on the left, not much I can do about it. Root x plus 1 times root x plus 1 is x plus 1. That's good. However, the middle two terms end up being negative 2 root x plus 1 minus 2 root x plus 1. So that's minus 4 times the square root of x plus 1. And then negative 2 times negative 2 is 4. So now I have to combine all my like terms, and I have to deal with the fact that I still have a square root in here. So 1 plus 4 is 5. I will subtract that over, and that ends up being negative 12 on the other side, because negative 7 minus 5 is negative 12. The good news is these x's are on opposite sides of the equal sign. When I subtract them, they cancel out. So that ends up not being as bad as it could be. So root x plus 1 equals 3. Now I square both sides. X plus 1 equals 9. X equals 8. I'm going to check this in my original problem. And when I do, the right side equals 1, and the left side equals 3 minus 2, which is also 1. So x equals 8 works. Number 14, we're not as lucky. We're going to square both sides. Root 2x plus 3 plus 1 squared, I'm going to write it out so it's a little bit easier for us to see. That ends up being 2x plus 3 plus 1 of both of them. So I have 2 more copies of the square root of 2x plus 3. And then 1 times 1 is 1. Squaring the right side is pretty easy. Now I want to get everything on one side. So I have 2 root 2x plus 3. Sorry, not everything on one side. Everything that isn't the square root on one side. So I'm going to subtract 2x over to the other side, and that will equal 5x minus 2x, which is 3x. I'm also going to subtract 4 to the other side. So 1 minus 4 is 3. Notice, I need to make sure that I take care of the fact that the order of operations is still important. I can't do 3 plus 2. The 2 times the 2, the 2 times the square root, that's happening first. That's order of operations. So I have to make sure that I am diligent about that. Now I'm going to square both sides again. Remember, 2 squared is 4, and the square root of 2x plus 3 is just 2x plus 3. The right side of this becomes 9x squared minus 18x plus 9. 8x plus 12 equals 9x squared minus 18x plus 9. And now it just becomes a bunch of doing what we've done ever since the quadratics unit. So 9x squared minus 26x minus 3 equals 0. If I factor this, I know I can put a 3 and a 1 in here because 3 is prime. And then 9, well, if I look at this, I need a 26 in the middle, so it makes sense to put a 9x over here and an x over here. Minus and plus will work. So I get x equals 3 and x equals negative 1/9. And I have to check those in my original equation to make sure everything works out. If I substitute 3 in, I get 4 on the right side, and 3 plus 1 is 4 on the left side. So that works. If I substitute in negative 1/9, it appears that everything stays positive. So if I substitute in negative 1/9, I get on the right side the square root of 4/9, and on the left side I get that would be the square root of 25/9 plus 1. No, that's incorrect. Negative 2/9 plus 3. 27/9 minus 2/9, that would be correct. So that actually doesn't end up working out because on the right side I get 2/3, and on the left side I get 5/3 plus 1, which is 8/3, and that doesn't make any sense. So this one doesn't work out.